right here, and you're good to go, I think.
So as you may have heard piecemeal, I'm Rob Ellenberg from Drexel up until a couple weeks ago, and now Carbide Labs LLC. So just give you a little bit of background about who I am. I've been at Drexel, as you can see, for quite a while. Started there in 2002 doing undergrad degrees, and I did the sampler program, so I got one of each of their degrees that I liked. I did ME and EE undergrad, and then a PhD because they had humanoid robots, which was a pretty cool field to be in, I thought at the time. And my dissertation was on studying the stability of humanoid robots, and you can see this still is from the DARPA Humanoid Robotics Challenge back in December. And I worked with the group that did the ladder climbing portion. As you can see, we almost got to the top, so we're pretty proud of that. And more recently, I'm a co-founder of Carbide Labs with 4 other guys from Drexel. We're all graduates of the Autonomous Systems Lab at Drexel, and what we're trying to get going is basically 2 efforts. We're doing product development, doing a desktop pick-and-place robot, or pick-and-paste as we like to call it, because we want to handle solder paste as well. And the other half of the business is doing training and consulting with the Tormach PCNC series, the 1100 and 770. All right, so to the topic at hand, why did we want to get into fixing the trajectory plan in the first place? And you can pretty much sum it up. The central problem that was in the LinuxCNC 2.5.3 and so on trajectory planner is that it couldn't handle short segments very well. And the wisdom for a while was, oh, just don't use short segments. You know, you don't really need them. But really, this is a fundamental part of a lot of different things. You've got engraving, sculpting, mold making, things like this. Anywhere you need fine detail and don't want to be machining all day, there's really no way around it. I actually put some numbers to this so you can see how important it is. And one of the constraints in the original trajectory planner is that no matter what blending you're using, for a specific segment, the speed is limited so that you have to be able to stop within one trajectory segment. So what you're seeing here, this table is just showing you that if you want to hit maximum machine speed, you have to have a segment that's at least, in the case of the PCNC 1100, about 0.2 inches. In the case of my little Shoreline CNC lathe, or CNC mill, sorry, it's a little bit smaller. And on some other configurations, it can get quite big. Like you'll need a long distance, big segments to be able to hit maximum speed. So you either need really coarse G-code, or you have to go slow. And your speed limit is basically the square root of your maximum acceleration times the segment length. One example that's been around for a while, that was around for a while when I first came into the community, was Steve Blackmore's example program here. And it has a lot of short segments, alternating straight lines and arc segments. And this is what it looks like when executed on the original trajectory planner. The plot at the bottom is the velocity in XYZ. And you can see there's lots of little dips. It runs at full speed for some of the time, but most of the time it's speeding up, slowing down, and it's not smooth at all. And this, of course, we can thank Sam for this wonderful test, and many others, as you've heard. And the top plot is just showing the correspondence to the arc length of each segment. So this, the top plot is just showing you for each line in the G-code, how long is that segment approximately. And there's a rough correspondence showing that when you have a nice long segment, you get a nice cruise at the speed you want, and when the segments start to get really short, the output velocity gets choppy as well. So when we're first looking at solving this, the standard way is see what everyone else is doing. We started looking at Mach 3 because that's very popular, and the basic answer was there's nothing really we could do with that code that would that would be effective. There would be so much effort in porting, and also later on, I'm glad we didn't use Mach 3 because Sam discovered some acceleration violations, in fact. So had we been able to port it even, it wouldn't have been as robust as we wanted. Similarly, Arise Robot Tech developed a limited jerk planner, which is definitely an exciting prospect. I know a lot of people are interested in limited jerk planning, and it has a lot of the pieces done, but the critical piece for us was that it was an exact stop implementation. As far as I could tell, they didn't really do blending using spline segments. So if you wanted to do continuous motion with G-code that wasn't already nice and clean and tangent, then it wouldn't really work for you. And there's other separate implementations we looked at for reference. TinyG does S-curves, but again, it was a very minimal implementation. It was enough for a 3D printer, but again, it wasn't enough to justify digging through their code and pulling it all out. And then of course, there was the quantum software, which there's been rumors of that. It was, I think, a previous product to Mach 4. It's more of a tech demo. In theory, it sounded very nice. They had high-order blending, so you could do very smooth, very gentle blending, but the problem was you can't get it. So it's pretty much, it doesn't help us. We also looked at, what alternative methods do you have? If we're going to do the blending ourselves, what techniques could we use? And industry standard seems to be the NURBS, non-uniform rational B-spline, which the qualitative conclusion was to implement blending with NURBS segments, handling all the velocity and acceleration constraints was challenging, which for reasons I'll get into in a bit. And there's other approaches that essentially they're all spline-based, things like Pythagorean photograph and Hermite splines, and even Bezier curves. Those, they offer, in theory, offer a lot of nice features, but are challenging to work with and were challenging to implement in LinuxCNC. And so the last option, which is probably the oldest, actually, in terms of when it was invented, is circular arcs. And so the value that, it seems a little counterintuitive why we elected to do circular arcs, but we'll get into the justification of that in a minute. So first off, I quickly want to touch on finite versus infinite jerk. There's been a lot of interest over the years in doing finite jerk planning. And the decision not to do finite jerk planning for this was a practical one. It was simply looking at the kind of machines that are typically used, which I'm saying that with broad strokes. Infinite jerk planning is good enough. For a stepper-driven stiff machine, it will get you a decent speed. Limited jerk planning would certainly be nice, especially in the case of machines that can accelerate very hard, large expensive VMCs. But the benefit isn't quite there for the sort of middle of the road machines. Okay, and so I'll probably just skip through this. Basically, the conclusion is doing more sophisticated blending methods is there are a lot of advantages, but in the actual implementation difficulties made it a little bit prohibitive, especially for me as a LinuxCNC novice coming into the scene relatively recently. So what we actually wanted to do with this was really just solve the look-ahead problem for LinuxCNC. And so, as I mentioned, we wanted to stick with infinite jerk planning, meaning we're going to use the traditional trapezoidal velocity profile, and just add on some velocity optimization so that you don't have to stop or be able to stop at the end of every segment in your trajectory planner. So to quickly brush up, I'm not sure how familiar everyone is with the details of the sort of trajectory planner fundamentals, so I figured I'd just throw it up here so you can see. So for a standard trapezoidal velocity profile, it's basically just 3 phases. You're accelerating as hard as the machine can go up until you reach the desired speed or the maximum speed that you can get to. Then, if need be, you'll cruise at a constant velocity. And then finally, you reach the third phase, which is where you decelerate back down to 0 velocity. And so this is the standard velocity profile in LinuxCNC 2.5, any version. And the way this works with respect to blending is that we can always, for a given segment, decelerate to 0 at the end of the segment. But if you start the next segment before you're done decelerating, then the sum of those two velocities will give you a smooth blend instead of a hard stop. And so you can see in the diagram to the right, what happens is if you start the start executing the segment on top before you finish the segment on the bottom, then it will have this effect of steering in a parabolic arc into the next segment. And so when basically when you're doing the planning for this parabolic blending, the big calculation you have to do is just decide when do I start blending? When do I start executing the next segment so that I satisfy the tolerance that I want? And the tolerance in this drawing is just indicated by the letter T, and it's just the distance between the parabolic arc and that corner. And so if you look at this from a velocity versus time perspective, you can kind of see what happens when you do the blending. So if you're to do exact stop, if you have two segments, the first one is in blue and the second in red, you would speed up, slow down to a stop, and then speed up again on the next segment. Versus the blend together, what happens is you basically overlap them. And as I mentioned, that means that the sum of the two velocities means that you don't actually have to slow down. And so you can, the net effect here is you get a cruise phase, an effective cruise phase, and you get blending sort of for free. You don't have to do an explicit blend arc to get this blend between two segments. So this approach is actually quite conservative, and the first thing we did to try and expand on a little bit is to say, well, if you can blend these two segments together, why can't you just make the acceleration within that blend higher? And that would look like the plot at the bottom here. And as long as the acceleration vectors are facing away from each other, in other words, if the two segments you're blending are almost parallel, then you should, in theory, be able to do this. The problem is to do this for every single case there's a lot of corner cases, and I'm not going to go too much into details because we didn't go down this road, but what it means is there may be potential here to optimize, but it very quickly gets messy. And so the sort of early speed bump we hit when looking at trying to squeeze more speed out of parabolic blending like that was that to do effective look ahead, you really need to know what the tangential acceleration is along the path. How hard can you accelerate and decelerate? And you need to know how long you have left in your path so that you know basically, do I have enough space at my current speed to slow down and stop? And the problem with parabolic blends as they were implemented is that you didn't have an explicit path. It was very difficult to look at it and say, okay, I know I'll be passing over this path of some length with a known tangential acceleration along that path. And so while it's not impossible to use parabolic blends and do look ahead, it makes the problem a little bit harder, especially if you want to do it offline.
So that's because you're not explicitly calculating the shape path. It's because you're simply starting to digest the next segment while you're continuing along the first segment.
Exactly. So the parabolic shape appears nowhere in the trajectory planner. It's just a consequence of doing two segments at once. So the circular arcs are advantageous in a few ways. They're probably the easiest type of blend arc to deal with in that they're very easy to parameterize by arc length, in that, you know, it's angle times the radius. Okay. And it's easy to parameterize any particular curve, like any arbitrary arc. You just need to know the start, end, center, and radius, and you're good. Another nice benefit here is that you can parameterize the tangential acceleration and normal acceleration separately. So if you limit your velocity on an arc of a known radius, then you can guarantee that I'll never have a normal acceleration higher than some amount. And so whatever's left over is I know that I can use that for tangential acceleration. And so I don't have to know exactly what my velocity is at any point to do trajectory optimization. So the beauty there is that's what I mentioned offline optimization before. What this means is you can basically do the optimization once every time you add a new segment, and then it's good. You don't have to touch it again until you add another segment. So the procedure that we follow to actually do this is relatively straightforward at a high level. So we basically start, the starting point for this is a pair of trajectory segments, typically the newest segment in the queue. So let's say, for example, you have a path queued up, a bunch of lines, say. You insert another line, and now you have a previous and next trajectory segment.
Can I ask a question about,
yeah, sure.
Is a segment just any straight move with arbitrary length, or is it the amount of distance the trajectory planner is looking at in the update rate of the trajectory?
So the way I've been using the word segment is just to describe, it's basically a G-code line. Oh. So line, arc, helix even, just some chunk of movement.
But it could be quite long.
Yes, it could be a very long line or a very short line. And so what matters is just for any pair of these segments, you look at them, compute the geometric constraints, find the radius, center, and endpoints, and then from that information, you can create a new trajectory segment representing that arc, make sure that everything lines up nicely, then trim the previous and next segments and add it in. And you basically repeat that every time you add a new segment to the queue, and you get overall you get a tangent path that follows, and it basically alternates line, arc, and so on. So this is what, drilling down into how we actually get some of those numbers. The circular blend arc looks basically like this. For the case of two lines, this is inspired by the same terminology used in parabolic blending. The same constraints basically apply. Fundamentally, we want to make sure that the path is within some tolerance of the original path. And so the circular blend arc that we would get is basically the green arc from Q1 to Q2. And so the information you see here is pretty much all you need to know to compute that and scale the radius to whatever you like. And so this slide is just kind of breaking down some of the terminology. We've got a tolerance, the radius, the tangential directions along each segment, the intersection point, which is the point where the two segments touch, and then the angle formed at that intersection. And it's labeled, the whole angle is theta, but what's drawn there is theta over 2. That's half of the intersection angle. So the vertical dotted line is basically a bisector of theta. And so what we want out of a blend arc is really just to come up with some circular arc that's tangent at Q1 and Q2. And we need to specify the velocity and acceleration in such a way that you're never violating the machine constraints. So the way we actually do that is you start by pulling the parameters, pulling some basic parameters out of the line segments. If you're blending between lines, you figure out what is the velocity that you're trying to achieve along this blend. Extract just some basic geometry you'll need to know later. These are, it's not so important to understand in detail, but basically just we're looking for the normal vector, which is along the vertical line, the dotted vertical line here. the binormal vector, which is perpendicular to the plane, and then the maximum velocity that we can reach. And that's basically the maximum of each individual velocity of the lines. So once we have that information, we then have to decide, well, how big an arc do you want? And the constraints on the size of the blend arc are pretty straightforward. We know we can't go past the end of a segment because then you wouldn't have any of the segment left, and that wouldn't work. You can't exceed the blend tolerance because, obviously. And within those constraints, you basically want to find the largest distance along the distance away from the intersection point, D, that fulfills all the constraints, your tolerance and being within what your segments allow. And so the equations at the bottom basically give you that result. You throw some trig at it, figure out, okay, how far can I be? Once you know your maximum distance as which I've the D sub geometry, the D based on the geometry limits, figure out how far from the intersection point you need to be. And then from that, you can derive, okay, what's the radius of that arc? And also, what's the velocity I can reach based on my maximum normal acceleration?
Excuse me, if I was making a punch in a gun, they got to fit. And I use this technique to make the punch. Well, got to fit. It doesn't sound to me like I'm getting exactly the same path through the two iterations.
You would if you set the tolerance.
It said, what's the biggest thing? It didn't
Right.
respect the tolerance.
Within tolerance. Right. That's one of the constraints. So where you see the first equation, it says D geometry.
Hold on.
Will the inside radius match the outside? Then I can't use it to make a punch in the gun.
But you have a tolerance.
I have a tolerance.
And you have an adjustable tolerance here.
But it sounded like the tolerance was, it couldn't go underneath the tolerance. It sounded like you found the largest D that fulfills the constraints.
Right. And the constraint is the green arc can't be farther from that point at the top, the intersection point, than distance t. So you specify, when you do G64P some number,
Right.
that's what t is.
Okay, so it respects the P.
Yes.
Yeah, we're cool.
And if you want, the other nice benefit of this update is it handles short segments really well. So blend arcs like this will be really big if you give it a big tolerance and draw with coarse lines. But if you use really short segments, then these blend arcs will be very small. So you can very tightly specify your curve, and it will follow it at speed. Okay. So everything up till now has been just dealing with two lines. And this is all math that would be familiar. If you're in high school geometry, you could go through this. It gets a little bit messier when you get to dealing with arcs, however. So the theoretical solution for dealing with intersections of arcs, you can actually compute an exact solution that, and your CAD programs do this, where you need a circle that is some distance away from point P in the middle. That's the green arc. That distance is T, and is also tangent at Q1 and Q2. So this is, while in theory you can get an exact solution for this, I banged my head against the desk for, not literally of course, but for a couple of weeks trying to figure out, like, can we do this reliably and not, have the computer be churning for milliseconds to do so. And you have a similar problem in what I call the convex case, where you're blending from the other side. The math is very similar, but it's still fundamentally you have three quadratic equations that you have to solve. And in general, you're not guaranteed that there is a solution. So the way we do it, since this exact solution technically exists, it's just going to be a lot of trouble. And the specific issue that I found after working with it is that the forward solution is easy. In other words, if you specify a radius, r, then solving the rest of this is very straightforward. If you, however, want to do the inverse solution, where you specify a distance from P, if you specify T in this diagram, then it's very hard to go backwards and get an R. So what we really have to do is just bypass that inverse solution, and then it's no problem. And so this is where, this is the kind of the secret that made arc blending possible. We take advantage of the fact that if you look close enough, you can kind of assume that the circular arcs locally act like lines. So what this diagram here is showing you is what happens when we take tangent lines at the intersection. Those are the lines in red. You can see they follow the blue vectors, which are the tangents at the intersection point. And then, since we make them lines, solve the blending problem as if you had lines in the first place. The result of all that will be a radius. You know, okay, I can, satisfying all my constraints, I have a radius of some blend arc. Once I have that radius, I plug it into the forward solution, and then I can figure out, okay, where would that circle of that radius be to be tangent to the two circles?
No, I think a slightly more conservative blend radius.
Yes.
In both convex and concave.
In this one gives it to you in concave because the lines always curve away from the tangents. So you're guaranteed to be less than the tolerance. Now, of course, this in theory means that if you're depending on it hitting the tolerance exactly, it'll be slightly off. But generally, when you're giving tolerance, you're specifying a bound. You're not specifying an exact path. So this worked very well. And you have a similar but slightly more complicated problem for the convex case. And so what we do here instead is figure out basically what is the worst case for the convex case, because what happens is if you see the 2 points towards the bottom, one of them is labeled C2, the other one isn't labeled at all. It should have a label, but it's the purple one. If you were to do a circle, if you were to try to blend with a circle bigger than that space, it wouldn't fit at all. So there actually is a maximum radius in this problem. So what we do to get around that is just draw a secant line over to the point where each circle is parallel to the normal axis, which this is kind of a lot to follow. I apologize. I hope the drawing helps. But once you could draw that, you cut that line in half, and that gives you a maximum amount of length to blend over. So you can't, when you're solving the problem with lines, you only can ever blend up to point D or to point F. And so the result is the circle there that, again, it's the same situation where it's slightly smaller than the exact solution, and so you won't violate your tolerance. And if the details of that solution are probably easier to understand if you're curious, the code spells it out pretty well, so if you have detailed questions about the math, I'd be happy to answer them later. So anyway, as I mentioned, to kind of summarize, since line blends are easy, we can just approximate everything as lines. And then as long as the angle between the lines is effectively smaller than the angle between the circular arcs, then we're okay. And so here, the solution to, once you have that radius, then the forward solution looks like this. So for the concave case, you just have these two quadratic equations which you can solve to actually not, you don't need the quadratic formula to solve it. It's actually relatively straightforward. But the end of the process, you get a center point, you get the intersection points Q1 and Q2, and then you're done. The arc line case is a little bit trickier, but you can take advantage of the fact here that since you already have a line, the problem is half done for you. So by using a coordinate system that is aligned with the unit vector, ooh, I can do this. This unit vector U2 and this normal vector N2, these are perpendicular. By writing everything in that coordinate system, you have these two equations here. And so you can basically just describe the radius and the distance to point Q2 along the line pretty much directly from your solution to that, your solution of the circular arc radius. So once you have R, the rest of it just kind of falls out. And so at this point, that's when you have those cases, the arc, line, arc. It works very well. There's a couple of caveats, though. You can only do this with coplanar segments. So in other words, just like these drawings suggest, these examples I've shown are all on the plane of the screen. But if that line was coming out of the screen toward you, then this completely breaks down and it doesn't work. And the reason that happens is because if you can imagine in this case a line coming straight out towards you from the screen, the tangent line coming away at Q1 actually kind of goes past it. So you have a line that's kind of coming away this way, and then a line that's vertical that they don't intersect at all. So you can't create a circular arc that joins those two. You have to do something more complex. You could add another line or make it a helix or something more complicated. But at that point, you're getting to the level of difficulty that you might as well just write a spline blend. Right. And the other subtle difficulty with this is that technically all circles in LinuxCNC, all circular arcs, are actually spirals to a small degree. And anyone who's ever written G-code that has I and J, they're actually spirals by a very small amount. And it's usually only like 1 or 2%. And LinuxCNC will actually throw an error if the spiral is too big. But this is just big enough that it messes with the solution to those, to Q1 and Q2, and the tangent directions. It's just enough that you get little constraint violations. And so the way we solve that is by pretending that the spiral arc is actually a circle. In effect, we cheat a little bit here and say that, okay, since the spiral is not very big, the amount of spiral, that's this S distance here, I can, instead of this perfect circle and dotted lines, the actual spiral is this black circle here. By just moving the center of an approximate circle down here to C1 equal to the spiral parameter A, and then increasing the radius by S, I get this pink local approximation to that spiral. So if you go far enough away, it'll start to diverge, but locally it's very close. And so if you do the circular arc calculations with this approximation circle instead of the original geometry, then you get a very, very close solution to something that's perfectly tangent. And it's hard to say quantitatively like what the upper bound is, but in all the testing, since we implemented this solution, I haven't seen tangent error to, I think it's like 4 or 5 decimal places in the logs. So it gets pretty close.
What is it about the trajectory planner in LinuxCNC that ends up creating spirals instead of perfect circles?
If you specify an arc segment with I and J,
right,
you're explicitly giving it a center. But if the start point and the end point are not the same distance from that center, you're making a spiral.
Oh, so some are true circles if you give it an exact IJ, but because there's a little bit of wiggle room there, which I can't just a truncation what the tolerance is.
So the way LinuxCNC handles it, I'm not sure what Mach 3 does, but the way LinuxCNC handles it is it's implemented as an Archimedean spiral by some small amount. So if you don't get IJ just right, you get a not quite circular path.
Is this a fault of the CAD system in the beginning?
Pretty much, yeah. It's usually you chop off decimal places. You know, like why do I need more than 4 decimal places? Well, this is why.
Or you can just use R.
Yeah, if you use R, right. Then the other problem is the center of your arc may not be exactly where you want it. And it's up to you to decide which error you prefer. So in either case, by approximating the spirals this way, we can kind of sidestep that problem. And since your typical arc blend that you care about, where you need this kind of performance, is a very, very slight intersection angle. The arcs come together very close to parallel, like in Steve's example, and in if you're doing a smooth kind of contour. You're very rarely doing a hard corner with two arcs. So you're very often in this kind of small region here. Okay, so that up till now we've talked about all the computation, and that's basically pre-processing. That happens when you add a new segment of whatever kind. It does all that number crunching, spits out an intermediate segment, queues that up, and now you've added 2 new segments to your motion queue. That's done. Now we wait a while, the trajectory planner is executing, eventually it comes up to, let me back up here. Before the trajectory planner executes, you've completed adding this new segment. Now what you have to do is figure out how fast can that segment go, not only considering its internal limits, which we've already calculated, the maximum velocity due to normal acceleration, the requested feed, that kind of thing. But also, are we close enough to the end of the path that we'll have to be able to stop? If you estimate that wrong, then you'll overrun the end of the path, and then, I don't know, potentially hit something on your machine, or bad things happen. So the nice thing, as I mentioned briefly before, because you're dealing with lines and circular arcs, you basically know what your maximum velocity, tangential acceleration, and arc lengths are without caring about what the motion state is. So completely independent of how the trajectory planner is executing, all I need to know is a one-dimensional version of that problem. How much distance do I have left to go? And along that path, what are my kinematic limits, the velocity acceleration? And so basically, you just iterate back from the start of the queue to solve this. There's 2 quantities you're looking for: the target velocity, which is basically the feed that you want to be following as you're going over that segment, and the final velocity, which is whatever velocity you have to be at the end of a segment so as not to violate the next one. And the way we compute this is by walking backwards at the end of the queue. You start by assuming that the final velocity of the previous segment equals the target velocity of the next segment, and then your target velocity, which in this case is the fastest that you can go and still decelerate to your final velocity, is given by that equation there. And so you step backwards in the queue until you either hit a limit where you can't increase the target velocity anymore, say you're already at a maximum velocity, or you run out of iterations, then you're done. And this process only has to be run once every time you add a new segment. And so that's the nice thing about this is this, we can talk more about the details later, but everything we just talked about up to this point doesn't really have to be in the real-time layer. It just was much easier to write it there. So it is, but it maybe shouldn't be. And so what this looks like, looking at the actual numbers, this is a simple example. For a completely arbitrary case, say you have a bunch of segments that are all 0.1 inches long, and you have tangential accelerations of so many inches per second squared. Velocity maximum is given here. If you run that optimization backwards, you start at 0, and you can see the numbers slowly increase until you hit the maximum, and then from then on it doesn't change. And so in this completely contrived example, you actually hit maximum velocity after 16 segments or so. So really, you don't have to do that much number crunching to get to the maximum speed with this. And in the stock setting is something like 50 or 60. And so you're not doing thousands of iterations every time. So at this point, I want to talk about a couple of small things that came up, little optimizations that we did along the way that got a bit more performance. One subtle thing that we found is that if you're blending, in this example here, say you're going from 1,0 to 0, 1 up to 1, 2. And you want to take this path. Trying to figure out the maximum velocity that this arc can reach is not all that easy if all you know is these two pieces of information, Vmax 1 and 2. Now, a particular quirk of the real-time side is you don't have the full information you might have if you're in the user side, say in Canon or something like that. So it's hard to know, well, how fast can you go? The naive answer would be to just do, okay, well, I take the minimum of these two velocities. Except the problem is, if you just look at these two numbers, they're both equal here, except your simple minimum will give you this answer that when you're coming along to this center point here and you're moving vertically in the y, you'll be going way too fast for the y-axis. The actual minimum is here, and it's clipped by this maximum velocity bound. So there's two methods to get around this. In general, there's going to be this rectangular prism in however many dimensions that tells you what the bounds of velocity are for each axis. So what we can do is say, all right, well, if there's going to be some sphere that I can inscribe in this prism, and as soon as it touches a wall, that's the biggest that sphere can be. And if I do that on a plane, it's relatively straightforward to calculate. Again, there's the details of it I'd be happy to go through are in the code, but it's kind of clutter at this point. So you can, if you just know, okay, depending on what the current plane I'm on, if I know what the maximum circle I can inscribe in that plane is, if I have my velocity limits making this rectangle, then I can say, all right, I know for a fact that I can always go that fast and I won't violate an axis limit. Another way to look at it is the altitude of the triangle connecting these two segments here. And so basically, if you get both of these will always be safe if you formulate them properly. And in particular, the altitude has to actually lie inside the triangle for that to be true. But so if you do both of those calculations, pick the larger of the two, you'll get a maximum velocity that's at least the minimum axis here. So let's say y is much slower than x. You'll, at worst, be going the speed of y. And if you can, you'll be going much faster. Say if this blue line was very close to the red line, then you'd have a speed that was very close to the blue and the red.
I'm mildly confused. This is for the case where axes of a Cartesian sheet do not have equal maximum velocity.
Yes, although it still applies even if they do, because the corner will always be faster. This maximum velocity is...
Oh, yeah. Gotcha. Sure.
Yeah, you can move 1 point, there's square root of 2 times faster at a 45-degree angle than you can in any one linear direction.
So you're either, depending on how you want to break it down, you're either always running at the speed of your slowest axis, or you run the potential of overspeed, going over speed. So using these two methods, you can get the maximum safest, the maximum safe velocity. So there's another couple things we put in that help out a little bit. They're not really major features, but they address little problems that came up. So one example is what's known as velocity ramping. This came out of a suggestion on the dev list a couple months back for a completely different purpose. Someone wanted to be able to do a smooth ramp from one speed to another instead of doing a trapezoidal profile where you accelerate at maximum rate. And I don't think it got a ton of attention, and it seems like kind of a rare use case. But the nice thing about velocity ramping is that you can actually skip an acceleration discontinuity this way. And by that I mean if you're moving along a path where the next segment has a higher desired velocity, but not much higher. If you're using trapezoidal velocity profiles, what's going to happen is you'll try and accelerate until you can hit that final speed, and then you're going to cruise at that final speed for the rest of your segment. And then you hit the next segment and say that one, the following one needs to go a little bit faster. You're going to have another step. So you end up with this stair-step pattern of accelerating suddenly up to your maximum speed and then cruising. And that'll give you, if that happens quick enough, if you have short segments, you'll get this hammering on your machine, which is like thump, 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 as it's accelerating and then not accelerating. But this...
Like a 4-man stroke limitation.
Exactly, that's what you're seeing here. This is a way to get rid of those extra jerks. And so what we do basically is say, all right, use this arc blend ramp frequency parameter, which I'll explain in a little bit. That controls at what point is the segment so short that you don't gain anything by doing trapezoidal velocity, and just ramped from the initial speed to the final speed. And so there you don't have, you actually get an acceleration that's, you can get a smooth change in acceleration, or at least I should say much smaller jumps in acceleration. Instead of going from maximum to 0, you're going a little bit and then maybe a little bit more, so it's very small jerks. Another minor feature as well, we ended up implementing a spherical linear interpolation to do the spherical arcs for blending, which you wouldn't necessarily see the difference at the interface, but what this does is makes a lot of the calculations in the back end much easier. And in theory, you could actually do a spiral that's much larger than what's currently allowed. So if you remember that spiral approximation issue, right now you're only allowed like a very small percentage of spiral, but using the slurp method, you can actually have a really large spiral and potentially still, using that local approximation, be able to do the same blending. So there's a chance, again, I'm not sure what value that is, but it gives you a little more flexibility if we want to go in that direction. So I think there was some confusion when these tuning parameters came out on the list a couple months ago, so I want to spend a little time and just clarify what I mean by these. And also solicit, as part of the Q&A, I'd love to know if there's a clearer way to do this. These parameters are just kind of what made sense at the time, but they're by no means the best way to do it. So the first one is obvious, right? The enable parameter, just turn on arc blending. The optimization depth controls how far back in the queue you want to iterate over. I haven't seen any reason to limit this, but if you're on a platform with very limited processing power, conceivably you could save something. You could save some power by keeping that low. In practice, because it's done only once every new segment, I don't think there's a need to limit it, but it's there. This parameter called gap cycles solves a subtle problem where if you're approximating an arc with all line segments, you can't blend and consume a line to an arbitrarily short distance. Because one restriction that I had to maintain for this is that you have to hit at most one trajectory segment per servo cycle. So you can't do more than 1,000 segments per second. So what that means is if you do arc blending and consume 99% of the line, so you have a big arc and a teeny little line, then that'll be a really slow spot because it might only be, a 10,000th of an inch long. So what this gap cycles parameter says basically is if it takes fewer than that many servo cycles to completely go through that segment, then it's okay for the trajectory planner to consume it entirely as part of an arc and throw it out. So instead of going arc, line, arc, you just throw out the line and have one big arc. And so that effectively smooths. So that effectively smooths out little jitters if you're doing contouring involving arcs. And finally, the ramp frequency, as I mentioned before, controls basically how short does a segment have to be to switch over from trapezoidal to ramped velocity. And what this basically is, the frequency is similar to, the reason I called it frequency is because it's somewhat similar to like the frequency that, it's like a cutoff frequency. So in other words, if you're going to be exciting the machine with these pulses at higher than this frequency, then don't. So the way you can think about this more formally is that the frequency is 1 over the number of time steps it takes to complete that segment, or the number of servo cycles. So if it takes you fewer than, say, 10 servo cycles, then your frequency will be, not the literal time steps, not number of cycles. So if it takes 10 servo cycles, then it's 10 milliseconds, and 1 over 10 is 100 hertz. So what it basically means is, if you don't want to do any limiting using this, you set it to 1,000 hertz, and then it will only kick in when you're 1 millisecond or less, in which case it doesn't matter. Conversely, if you set that to a very low frequency, like 10 hertz, then it will, segments that take less than 100 milliseconds to execute will be switched over to ramped velocity. The big reason for this is to prevent it from, like, you get real nice smooth performance if you're using the ramped velocity and fine detail contouring. And then if you have a rapid move out of nowhere where you have to go several inches, if you're still ramping, it'll take forever to get up to speed. And you'll be staring at it, scratching your head like, why is it going so slow? So this basically gives you the option to kind of have the best of both worlds. And so to summarize, this is the difference. This is what we started with, the LinuxCNC 2.5.3, and this is what it looks like now. This is Steve's code, the contour, and we can go up to and maintain maximum speed essentially over the whole thing. Again, this is, of course, thanks to Sam's excellent testing. So a little bit of bookkeeping at this point. If you're interested in poking around on the code, seeing where all the stuff is, it's slightly rearranged from what it was in LinuxCNC. The TP stuff is moved in this new folder called TP. Broken down in basically the same way it was before: trajectory planar, segments, etc. However, I refactored the headers so that the fundamental types, the constants are in their own headers, which are used elsewhere, and then the functions are in separate headers. And then the really nitty-gritty math that's used to calculate blending specifically and spherical arc stuff is each in their own source file. Finally, there's something that may be more relevant to general users, developers. There's one of the things that really annoyed me looking through the old code, the code that hasn't been touched in a while in LinuxCNC, is that there's a ton of blocks of 9 lines of code copying over X, Y, Z, A, B, C, U, V, W. Every time you want to do anything with an EMC pose data type. And that's what stores all 9 axis positions. So I just wrote some basic functions in this emcpose.c library, adding, subtraction, copying, I think. A couple other things, just so that you can eliminate those blocks. It's not perfect, but at a minimum, if we start writing code using those functions, then what it means is if we change the implementation of emcpose later, then you're just swapping out what the function does, and it doesn't completely clobber your old code. So hopefully that'll help move things along as we're giving this an overhaul.
Can the queue be written to a file? Can that file be used?
The queue, as in the trajectory queue?
Yeah.
Why
All the little waypoints on my track.
Why would you want to write it to a file? What's the use case? Oh, so you can backtrack it.
I got a pointer and I just go up, down, up, down, up.
Well, it depends on how ugly you want to do it. So part of doing all this, if you look at this code, you'll see it peppered with debug statements that by default do nothing. They're compiled out. But if you enable the debug flag, it basically spits out almost every variable in the arc calculation and a status line every time the trajectory planner runs. So if you really want, you can log every single position every time that way. Now, if you want to go to that point, you can also just use this. I think it's HAL Sampler does that as well.
I don't know that that actually could, that it ever had the ability to look at what was going on in the queue. The queue has been Blackmore. But that's just my look at it. My real point would be to be able to inject little chunks of motion inside of it, because I do not do wire really nice. So I got to do what's called orbiting, things like that. It's translations. So, but let's move on. You satisfied my point about it. It is available.
How long back would that typically go? Like in seconds or distance?
Minutes.
Minutes.
Oh, in minutes and distance, minutes in time and distance, tens of thousands of inches. Like very, ECAM is incredibly slow. So the magnitude of distance is very small. So the magnitude of time is
1,000 positions a second, so with the minutes of 60,000.
Imagine the central point that the tool resides at right now. And what I want to do is I want to do 10,000s in a square orbit around that center while I'm going 10,000s deeper. And then I want to reiterate it at a different power level that's 11,000s and then at 12,000s. Which makes my tiny tool full size. Okay.
It seems like you could do that. You may be able to hack something with the Q, but I would look first at a G-code level solution. Like if you know what that path has to be, you might be able to write it directly in G-code or tell a CAM program how to do it, or even script it. And that might maybe not even necessarily you personally, but someone might know if you can describe that path.
We are not at a position at a time. And that's the premise of LinuxCNC, is that you're in position on time.
Yeah, the problem with EDM is that you have to be varying the seat height, right?
I'm jittery, doing this
But you
little
want to be
cha-cha
doing
while
it
I'm approaching the position.
Mm.
Yeah, you're right.
I think there may be a better solution.
That's why I retained what I have.
But
I only let EMC pose, and then I work.
yeah, decoupling the z-axis from the x-y.
I don't.
The one thing, so I can think.
I don't want to really dwell on this because I don't think it's important that anybody knows.
Well, we should talk later about it. But I think if nothing else, there may be some fundamental features you could add that would at least make it possible. So, and all right. So at this point, we're basically at the end. There's a couple of things that I would consider future work. There's been some discussion on email lists and such. I know a lot of people would love to have this generalized to all 9 dimensions. Right now, you can really only use this for X, Y, and Z. And the good news is to do this with just lines is almost the same in 9D as it is in 3D. Because the abstracted version of the geometry, you just need lengths and angles. You don't really care that it's 9-dimensional. One small problem there is that for the math to actually work out, you really want to work in some kind of normalized units so that one axis having, say, if you're working in degrees on one and inches on the other, then if everything is limited by the smallest number, then one axis would go 5 degrees a second or something ridiculously slow. But with those prerequisites, it would be relatively straightforward to do line-line blends in 9D. Now, arc line and arc-arc blending is not the same thing. That would basically require another level of work on top of it. So I would say that's far future if ever, but this case at least is possible. Similarly, if we really want to get more jerk limitation, we could do some more kind of crude hacks on top of it. For example, there may be a way to do a parabolic blend on a tangent segment already, and what that'll effectively do is mix between segments that are going the same velocity, but don't necessarily have the same acceleration instantaneously. So you'll get a smooth transition to eliminate cornering acceleration. So say you're going around a circular arc and you hit a line, that you could do something like that to soften that corner. It wouldn't solve the issue of the tangential jerk, from accelerating or decelerating. But perhaps a combination of this plus ramped velocity might be good enough for some applications. And finally, I know there's been interest in having run everything backwards. And I think, as Sam pointed out, I was famous for saying it shouldn't be too hard, a couple weeks. And so I think what it would take to do that would basically mean the thing that I can see, the big limitation right now is we're missing some data that we would need. You basically need to know the equivalent of final velocity, but for the previous segment instead of the next. And also the ability for the motion planner to switch signs so that it can understand negative velocities. So that immediate implementation is not too hard. I'm not sure what else it would take at this point, but there's no fundamental barriers there as far as I can see. All right. And so I also want to give some basic thanks, of course, to Sam for all of his testing. To Michael, of course, for a lot of advice early on, and to the LinuxCNC community as a whole, which when I was first starting out at this, I knew essentially nothing about it, and everybody really helped get me up to speed. So I consider this in a lot of ways a team effort. And yeah, that's it. I guess at this point we can start Q&A.
Yeah. Thanks, Michael. And thanks, Robert.
You may have some questions on the G-chat thing too.
What would happen if we learned programming tangentially from the beginning?
So make sure before you answer the question that you repeat it, because as I got on email, folks listening to this online are only able to hear you.
So the question was, what happens if your G code is already tangential? Then it detects that. There's a step when you're adding the new segment. It checks if it's already tangent, and if it is, it does nothing. And it's as if the blend part was already done. So if you give it perfectly tangent code, it'll just pass it right through and run the optimizer.
My original background was mold maker, and I fell into working with Angie for wire EMs, and we had to do everything tangential. So I kind of got used to it. I wondered what the effect was.
Yeah, and actually that would let you do things. You can do cases that the arc blending can't handle. For example, if you have a helix, if you can figure out how to make your helix tangent to your path, it understands that and will follow the tangent path and deal with it. So, if you're doing a helix and you have a line coming out that follows it, and there's actually an example in there that shows that behavior. So that's one way to get around the limitation. All right. Well, I guess I answered that question. Should I summarize this question?
The comment with all the little bit of testing I did, plotting what Mach was doing. Mach seemed to do parabolic blending, but it keeps adding segments. However, their tolerance is also, it isn't, LinuxCNC is nice because you can say, I want to be within 10,000ths of the path. Their tolerance seems to be when the blend starts on the arc segment, which is totally odd to me. But I don't know how you would know how that actually follows the path. But
what it means is you have a very varying tolerance. So your tolerance would be really big because it's distance along the edge. Like if you have an edge that's perpendicular, that's a big tolerance. If you have an edge like that, then it's very small.
You might repeat the commentary.
Oh yeah. So Sam mentioned that Mach 3 doesn't constrain tolerance in the same way that LinuxCNC does. So while LinuxCNC gives you the option to specify how far from the trajectory you want to be, at worst case, Mach 3 specifies how far from the end of the segment you want to start a blend. And oh, the other thing about Mach 3 that I showed in one of the tests is that I don't know how or why, but they don't obey maximum velocity constraints. And I figured that out by setting up a G-code program that went back and forth over 10 inches a couple of times, and figuring, based on the acceleration limits, you know, it was 15 inches per second squared and some maximum velocity. I figured out exactly how fast it had to go, and it went over that speed by about 5%. Just now, I don't know how consistently it does that, but I knew that was the case. It wasn't just a short blip, because when I ran that program on Mach 3 with the same limits, it came out 3 seconds slower. It was like 45 seconds instead of 48. And the LinuxCNC version was exactly right. So they're doing something behind the scenes, and I don't know how they get to that point, but the more, especially with Sam's testing, like, I trusted less and less. And there were cases like, Sam, you found, it was acceleration violations, sometimes big ones,
Huge.
going around corners, like half again or double.
As you increase the velocity, like we're talking 500 inches per minute, and say acceleration of 30 inches per second squared, as you approached those limits, it seemed to violate quite a bit, like into the 100 inches per second squared.
Right. So for people listening, what Sam said, if the as you get faster and accelerate harder, you get violations of 100 inches per second squared maximum instead of, say, 30. Yeah. So very significant momentary violations. And I know, sort of qualitatively, I remember there were programs that we ran on the our lab's PCNC 1100, where for some reason it would sound really rough. There'd be these random thumps and clunks that didn't seem like they should be there. And while I have no proof, I suspect that those two might be related.
So I have a question for Sam. I don't know if people will be able to hear on the microphone. Maybe Rob can repeat it. But when you were looking at the step outputs of Mach 3, this is a parallel port implementation of Mach 3. It's sampled by the FPGA on the Mesa board. Right?
The Mesa card allows you to set the encoder counter up to read that direction.
So how were you able to determine, I mean, having looked at a pulse stream on an oscilloscope for a parallel port pulse machine, if you have a 25 kilohertz update rate and you're commanding a 20 kilohertz pulse stream, there's crescent and jitter.
Yes.
Right? How are you able to distinguish between an acceleration violation that's a pure acceleration violation and just acceleration violation?
Right. Because I was looking over a longer period.
What period?
I think I was looking over 70 or 60 milliseconds.
So these are
right. Otherwise, it was noise. Yeah. Otherwise, it was noise. I was using the velocity output from the Mesa card, which is really good, and then I was using that and doing a DBT of the velocity. But I had to do it over, say, 60 milliseconds. Otherwise, it looked like noise. And I would compare it to LinuxCNC, so I'd have an idea, okay, LinuxCNC is staying within a percentage. So I kind of had
compared this to a parallel port implementation of LinuxCNC.
Yes.
Yeah,
exactly. Interesting. It was fun.
So to repeat it for the webcast, there's jitter in the output from Mach 3 due to Bresson-Hemming. So Sam basically tested over a large window, something like 70 milliseconds, and the violations appeared even at when you average over that window. So it wasn't due to just noise. Just had another thought. Oh, right, that's what it was. So I assume most everyone's probably familiar with the naive cam detector feature in LinuxCNC, where if you're doing G64 and you specify the Q word, that basically says how if deleting the current segment will give me an error of less than Q, then delete the current segment and make it one big line. So imagine you're drawing, a typical example would be, say you're drawing an arc out of line segments and they're very, very, very short. As you go around the arc, let's say you advance over several segments, but deleting those segments, the chord error, if it's less than, say, 1,000th of an inch, and you specify Q as 1,000th, then it will just delete them, and you'll get fewer longer segments. Now, for that to be of any use in the traditional, the original trajectory planner, you had to do pretty big tolerances. And in fact, the default case, I don't know if it's documented, but there was a discussion a couple months ago on the dev list. If you specify a P word, that implies the same Q word. So if you specify P of 0.01 inches, you're also saying Q 0.01 by default. So you're deleting any segment that would give you an error of less than 10,000ths of an inch. So that could mean if you happen to have a big long traverse and then a couple of short moves, it may well delete those short moves and you'll get this angled traverse instead of a straight horizontal one. Or not even a rapid, just like say you're doing a long straight cut. Imagine you're cutting a flat edge that you want to be perpendicular, and then you go around a corner and there's maybe some detail. That whole long edge might have drifted at the endpoint by as much as that tolerance. And you would never know that if you didn't know what those defaults were. So one thing I'd like to do that I'm not sure what if LinuxCNC was happy with that, but I'd like to put it to you guys is to make the default be not to do that, or possibly have the default be a fixed, very small number, perhaps 1,000th of an inch, or 0.01 millimeters. The reason for that is small amounts of naive cam detection are actually really, really helpful at fixing that very short segment problem. So one of the issues that I mentioned before is that you can't exceed 1 segment per second. So if the segments are really short, you have to go really slow. Even per cycle. Yeah, per second, sorry. So if the segments are really short, you have to slow down, even if kinematically you're doing a very gentle path. So the naive cam detector, if you give it a strict value, 1,000th of an inch or so, will clean up really rough cam, but not make big gouges. And then once you have segments that are several thousandths of an inch long, say, then the trajectory planner will be able to follow it much better. And that's important because really, if you're exceeding if you need to go faster than 1 segment per update, you're not going to get that detail anyway. So like if you try to do something like, well, maybe I want to quadruple my servo loop so that I can do smaller segments. Really, at that level, you're pushing the machine so hard, you're really not going to be able to get that kind of performance. So just a teeny little bit of naive cam detection can solve essentially all of the that sudden slowdown problem. And you can see the difference on any of the NGC code, in particular the test G code in the Circular Arcs test folder. There's a bunch of engraving programs that run really slow if you have no naive cam detection. You give it 1,000th of an inch or 2, and suddenly the speed is like 20 or 30% faster, with essentially no change in detail. So that was kind of a surprising result. And when you're tuning and working with your programs, that's something to keep in mind.
Do people people should do this. Every machine tool has a potential acceleration and radial acceleration. And it should be known and told to the control system so that it doesn't violate that. Mathematical limits are one thing, but the ability of a machine to turn a corner at a speed is based on the construction of that machine, its quality, its bearings, its weights, its rails, and you should be able to put a glass of water on the corner of that cabinet and watch that machine move around and at least not spill the water But what you're looking at is the ripples on that water surface. It's a little bit better than biting on the machine to get a good feedback for how stiff it is. I don't know that people are actually doing that or not. What do you guys do here at Cormac to find the potential of your machines?
So the question was, to boil it down, how do you figure out what the acceleration limits actually are? It's one thing to just call it a number, but what is the limit of the machine?
I could, if we have to describe that to you, we also wrote a paper that covers a lot of that. This is a Series 3 white paper. Had a lot to do with picking the motor technology for the Series 3 mills. But I don't know if we want to have a trajectory plan.
I'd like people to know that you cannot tell a machine what its acceleration is. You ask the machine what its
Yes, correct. Yes.
Okay.
So any other questions for the broadcast?
We should probably ask the web and then wait at least 45 seconds.
Yeah, if there are any questions that you guys are trying to send in, I'm not sure. I'm not seeing any in the Q&A app, but there might be email, so we'll wait another minute, I guess.
Okay, we have 60 seconds. I'll go off topic. Dinner is when it get done, 6 or 6:30. Is everybody going to hang around for dinner on the patio? Any vegetarians or special requirements? All right. Here.
You were asking about those parameters for the INI file. Are those not parameters that you would want to pass through the G code so that then you put that in the post processor depending on what type of operation you're doing?
Do you mean
Naive cam detection?
No. So those are.
It would be easier if you could change them. Oh, sorry, right. So the question is, would it not be better to put the tuning parameters in either G code or possibly HAL, something like that, so that they're accessible rather than in the INI file, which is kind of a pain to edit.
And you have to restart the application.
You have to restart. And the answer is yes. And honestly, I'm not really sure why INI files are even there at this point. I mean, in the sense of like static one-time storage, it seems like an option of convenience rather than the best design. Like ideally, you'd be able to change all of it on the fly. Like there should be knobs in the machine where you can just tweak it. Knobs, you know, not physical, of course, but and so there actually Dewey Garrett made a branch a couple months back to set these pins and the maximum acceleration, those kinds of things, as HAL pins. I haven't, unfortunately, his branch got out of sync with a bunch of fixes that I did, and I just haven't had the time to bring it up to date. But I don't think it's diverged in such a way that we couldn't stick that back on, and then you could just use HAL.
He was working on like analog servo tuning.
These parameters, he just came up with a way to make them be HAL pins instead of INI settings. So you could change it. And there's actually a really cool demo. I think there's a video on YouTube of a trajectory planner test GUI where you can set all these on the fly. So you want to see the effect of turning down the ramp frequency, you just change the setting. Which
is pretty much all, the analog circuit is pretty much all available as HAL pins.
To change
PIG, FF0, 1, 2, all that. All
that's
that.
nice.
There's calibration made, pull that out, all that does go in and get the HAL pins.
I got some new Skylight, they're old second-hand Skylight drivers.
Calibration made, they'll send you 2 hours.
Great.
all right, so we're going to stop broadcast.